Alright, so I messed up a little bit at the end of the last video, and also the video bled over a little bit past the 20-minute mark, and so it looks all choppy and stuff, but anyways, there was an issue in my notes that I managed to figure out as I was going through the video, and the issue was that I had CD and gamma flipped in this proof here. So here, I don't know where I'm going to have to restart the video or restart the proof from. So you know what? Let's just start from the beginning. Let's just start from the beginning. So we have our lemma: AN is generated by 3 cycles, and 3 cycles are conjugate in AN if N is greater than or equal to 5. Here, AN is generated by 3 cycles. Okay, so I said N is greater than or equal to 5 over here. Here, you need a restriction on N as well, and you need N to be greater than or equal to 3, and I'll leave that as an exercise for you. So to prove this, we first prove the first statement. Certainly all 3 cycles belong to AN. Because of this, we can write any 3 cycle as a product of transpositions in this manner. Okay? And so now, if we have any sigma in AN, we want to write it using 3 cycles. So first we write it as a product of transpositions, and we write 2p here to emphasize the fact that this is an even number of transpositions. Now let's take any pair of transpositions. Can we write that pair using 3 cycles? Well, if they intersect at one index, say A, then it's equal to ACB. And why is this? Here if you start at A, it'll go to C, and then it stays there. If you start at C, then it'll go to A and then to B. If you start at B, then it will go to A. So it agrees out with this. What if they're disjoint? They don't intersect at all. Then, let's see here, this sends A to B, B to A, C to D, D to C. Where does this send A? A will go to B, and B will go to C, which will go to A. Here, C will go to D, and D will go to B, which will go to C. And so, there you go, you have that equality. Obviously, the last scenario is that they intersect in both indices, but then it's just the identity. And so you can write sigma using the trivial permutation and 3 cycles, because you take every single pair in here and you write it either just as E, or you use 3 cycles, and you can get through all of sigma that way, and there will be no transpositions left over because there's an even number of transpositions. So that does the first part. Now for the second part, we suppose N is greater than or equal to 5. Suppose alpha is A1, A2, A3, and beta is B1, B2, B3. These can intersect, that's fine. And they're 3 cycles. What we want to show is, to show that they're all conjugate, we want to show that we can conjugate alpha by some 3 cycle. No, we want to show that they're conjugate in AN. So we want to prove that we can conjugate alpha by a permutation of even order and arrive at beta in this manner. Because what we know is we know that the conjugacy classes are precisely the cycle types, and that if you have 2 permutations whose disjoint cycle types are the same, then they're conjugate by some element in the permutation group. And so we know that there exists some gamma in Sn such that conjugating alpha by gamma will give you beta. But we don't know if gamma is in Sn per se. So if it happens that that gamma is an even permutation, then you're good, because that means that gamma is contained in AN. But what if it's not? Then what we need to do is we need to choose 2 more indices. We'll call them C and D, and we have to choose them such that they're not equal to B1, B2, or B3. So then what happens? Then you take gamma and you multiply it by CD, and it becomes even because you took an odd permutation and you multiply it by a transposition, and so it can be written using an even number of transpositions. Okay, so that's even. And what if we conjugate by this element? And this is where I messed up. This is where my notes were had an issue, is that you have to conjugate by CD gamma and not by gamma CD. Because what happens is if you conjugate by CD gamma, then you get CD gamma alpha CD gamma inverse. But you write the CD gamma inverse as gamma inverse CD, and then you've got this gamma alpha gamma inverse on the inside here. And that is equal to beta. And so you use that to your advantage. So you look at any index, and you suppose, first let's suppose that our index is neither C nor D. Then where is beta going to send this index? Well, if it's neither C nor D, then, well, where's this thing going to send the index? So if the index is neither C nor D, it'll go right past this CD, and it'll go right past this CD. So the only thing that it goes through is this gamma alpha gamma inverse. But we know that gamma alpha gamma inverse is beta. So this gamma alpha gamma inverse on the inside will send it to the same place that beta would send it. And so these two things are equal on indices which are neither C nor D. Now if we look at an index that is C or D, then what's going to happen? We know that CD is not beta 1, B1, B2, B3, so it's not in beta. So beta doesn't move C, beta doesn't move D. So therefore alpha or gamma alpha gamma inverse doesn't move C, and it also does not move D. So let's see what happens to C here. Here C goes to D, and then it goes right through gamma alpha gamma inverse, and it comes out here where it gets sent back to C. And so C got mapped to C, and that agrees with beta because beta doesn't contain C as one of its indices. Similar thing with D. D will go to C, then it'll go all the way through here, and then C will go back to D, and so D is fixed, just like it is for beta. And that shows that we have this inequality, and so therefore we can find some element of AN such that conjugating alpha by that element gives you beta, and therefore all three cycles in AN are conjugate in AN. That completes our proof. Note that the reason we needed AN to be greater than or equal to 5 was that we needed to choose C and D to not be in B1, B2, B3. And you might think, oh, well, you know, maybe that's just something that we needed to do in order to make this proof work. Maybe you can, maybe it's the case that three cycles are not, maybe it's the case that all three cycles are conjugate in smaller n's. I'm pretty sure this is not the case. I'm pretty sure you need, I forget the details, but I'm pretty sure you need n to be greater than or equal to 5. You certainly need n to be greater than or equal to 5 to have simplicity, and I think you prove simplicity of AN using this fact that all three cycles are conjugate. And so I think it really is necessary here. But anyways, yeah, that completes this result on permutations.